Hi, my name is Sergey Levine, and today I'm going to talk about generalization and the role of data in reinforcement learning. So, at a very high level, what makes modern machine learning work is having access to large and diverse data sets and training large and high capacity deep neural network models. This basic recipe has been tremendously successful across a range of fields, from recognizing objects in images to translating text to recognizing speech. But at some level, all machine learning that is actually used basically amounts to a kind of automated decision making. This is not the conventional way of looking at it, but hopefully I'll be able to persuade you that this is true. So typically, when we think about prediction problems, like recognizing images or translating text, we generally frame them as prediction problems. And we make a number of assumptions that make them kind of easy. For example, we assume that the data points are independent. The class that you predict from one image won't affect what you see in another image. You assume that outputs don't influence future inputs. And you also assume that the ground truth labels are provided to you at training time, and all you have to do is learn to generalize from those labels. A lot of problems are explicitly not like that. So if you want to be able to drive a car, control a robot, manage inventory levels, trade stocks, and so on, these are explicitly decision-making problems. And they often don't satisfy these assumptions because the current action will influence future observations, the goal is to maximize some utility, basically some reward function, and the optimal actions are not provided. Like if you knew the optimal decisions to trade stocks, you would have all the money you could want. The problem is that you don't know what those decisions are, you have to figure them out. But that's actually not the point I wanted to make. The point is, these are not just issues in problems that look like control. In many cases, real-world deployment of machine learning systems, the first kind, the kind that are making predictions, has feedback issues that make them look more like the second kind, make them look more like decision-making problems. For example, let's say that you build an app to predict traffic. The predictions made by that app will be used by people to decide where to go when they drive their car, and that in turn will affect the traffic. So the outputs that your supervised traffic prediction system is producing will affect future inputs, and that violates one of the assumptions of regular supervised learning. I would go so far as to say that virtually all machine learning systems that are actually useful are useful because they make decisions. They make some prediction that somebody's going to act on, that's going to influence the world in some way, and that will create these feedbacks. So if ultimately machine learning is always about making a decision, why don't we treat every machine learning problem as a decision-making problem and utilize the mathematical framework of decision-making, which is reinforcement learning? So basically, why aren't we all doing reinforcement learning? But there's actually a reason for this. There's a reason why we don't all use RL, and it's because reinforcement learning basically amounts to two separate things. First, it's a framework for learning-based decision-making. That's what we want. It takes us from a setting where we look at an input and predict a ground truth label to one where we look at an input and predict an action, predict a decision that influences the future. But reinforcement learning is also another thing. Reinforcement learning is a framework for active online learning for control. This is the classic kind of diagram that you see, for example, in the Sutton and Bardo textbook. You have an agent that interacts with the world, receives some reward, updates its behavior, interacts with the world some more, and repeats this process. So here you would interact with the world, collect the data, update your model, throw out that data, interact some more, and repeat this many, many times. Almost all real-world learning problems look like the thing on the left. They look like decision-making, and hopefully I've made the argument for that. But almost all real-world learning problems also make it very difficult to do the active online thing. Imagine that, for example, you are doing inventory management for a large corporation with thousands of warehouses around the country. Well, you really don't want to be making arbitrary decisions to change levels of inventory just to explore and find out what kind of reward you're going to get. You probably want to start from a pretty reliable place. You certainly don't want to do reinforcement learning from scratch to learn to drive a car and figure out your driving policy by bumping into things. You want to be smarter than that. So what this amounts to is we really want the stuff on the left, but we kind of don't want the stuff on the right in many realistic cases. Okay, but at this point you might say, well, but reinforcement learning kind of works, doesn't it? We've seen all these examples with video games, robotics tasks, even beating the world champion at Go. But there's a big gap between the kinds of domains where reinforcement learning has been successful, the ones shown on the left, and the kinds of domains where supervised machine learning methods have been successful, shown on the right. In the examples on the right, they're characterized by open world complexity and diversity. Classify any image on the internet, translate any text, recognize any speech. Whereas all the examples on the left are closed-world environments. The rules of Go are well known and well characterized. The Go playing robot doesn't have to worry about someone spilling coffee on the Go board and figuring out what to do with that. So there's an enormous gulf, and it's not a gulf of how difficult the task is, it's a gulf of diversity and complexity. And of course, the way that machine learning methods deal with that is they use lots of broad and diverse data. The reason that that image classifier can recognize any image on the internet is because it's been trained on so many images that it will generalize. But it's very difficult to do that in RL, in this active learning paradigm, because if we have to recollect the data every time we update our model, basically if we collect an ImageNet-sized data set, update our model, throw it out, and collect another ImageNet-sized data set just to take one iteration, that's never going to be scalable. So if we want to do RL in the real world, we have to make it more data-driven. We have to preserve the benefits of actually learning to do decision-making, to reason about future consequences of our actions, but remove the need for active online data collection. So we have to kind of make RL look a little more like supervised learning. So classically, on-policy RL has this framework where we collect some data, update your model, and then repeat. And what we want instead is offline reinforcement learning, where we have a data set that has been collected before, maybe historical records of how inventory levels have been managed in your warehouses, or previously collected data of humans driving vehicles. The data is going to go in a buffer, and we'll learn a policy from this buffer without any additional interaction with the system, without any additional online collection. And if we can do this and get a policy that we can deploy and get good performance, then we'll have a much more scalable solution that could actually generalize to real-world problems. So that's the essence of offline reinforcement learning. So ideally, the workflow that this kind of procedure would enable is one where first you would collect a data set using any policy or mixture of policies, such as humans performing a task, some existing hand-engineered system performing the task, or maybe even random behaviors, or maybe even any combination of the above. And this would only be done once. Then you would run offline RL on this data set to acquire a policy. And you can think of this as the best policy that you can get from the data that was provided to you. And then you would take this policy and deploy it in the real world. And if you're not happy with how well it's doing, you could just go back to step 2, but not have to recollect all your data. Just reuse the data again, but train the policy differently. Or if you believe you don't have enough data, you can go out and get more data and increase the size of your data set. These kinds of techniques could be very valuable in settings where active data collection is impractical, like inventory management, prescribing a treatment plan for a patient, scheduling the course of scientific experiments, stock trading, and of course also my field, which is robotics. All right, so that's kind of the good news. That's what in principle could be enabled with effective offline RL methods. But why is offline RL hard? Like, why are these problems not already solved even by existing algorithms? Well, the fundamental problem is that doing offline RL requires answering counterfactual queries. So imagine that you're doing autonomous driving, and your training data consists of humans driving cars, and they drive the cars pretty well. Not perfectly, they sometimes swerve side to side, don't make every turn perfectly. They sometimes, roll through a red light or something. But on the whole, they're not going to do really crazy things. They're not going to just like randomly swerve off the road and crash. Your offline RL algorithm needs to determine, for other actions available in states that it's seen, actions that were not taken in the data, are those actions actually good or bad? So you've never seen a car go off the road. Is that a good idea or a bad idea? And how do you know if you haven't seen it in the data? So of course we know that it's a bad idea, but the algorithm has no way of knowing that with the data that it has provided. Online RL algorithms don't have to worry about this because they can simply try this action and see what happens. But offline RL methods have to somehow account for these unseen or out of distribution actions, ideally in a safe way. Basically, if you truly don't have enough evidence to figure out whether an action is good or bad, you probably shouldn't take it because you don't know what will happen. But at the same time, you still have to make use of generalization to come up with behaviors that are better than the best things seen in the data. So maybe you've seen left turns at intersections, just not this particular intersection. Well, here you should be able to generalize. You should be able to figure out that here, a left turn is possible because you've seen left turns in other similar situations. But a left turn in the middle of a straight street, that you shouldn't even consider because nothing you've seen can possibly prepare you for that. So that's a tricky problem to deal with. All right, what do we expect offline RL methods to do? Well, there's some bad intuition, which is that offline RL is like imitation learning. So maybe you've seen some good trajectories that get from the start of the goal. So here, green is start, orange is goal. And what you want to do is basically copy them. That's bad intuition. We can expect a lot more than that. Although, even in the case where you have these demonstrations, offline RL can still help for a very technical kind of theoretical reason. But a better intuition is that offline RL is kind of about getting order from chaos. Maybe you've seen a variety of behaviors that kind of go all over the place. And what you want to figure out is the best behavior that is within the support of the data. So you want to take pieces of behaviors that you've seen and recombine them in a way that ends up being better than any of the individual behaviors by themselves. One kind of very rough schematic view of this is this idea of stitching. So imagine that this is a navigation task, and you've seen in your data set some trajectories that go from A to B, and some other trajectories that go from B to C. That should be enough for you to figure out a trajectory that goes from A to C. Right? The information is all present there. But you can take this idea just even further. This is simply the clearest instantiation. What if you have a huge number of trajectories that are all suboptimal, but each of them is good in some place and bad in others? Maybe you're doing stock trading, and you have humans trading stocks, and maybe there's hundreds of them, and some of them are good in certain situations, but very bad in most situations. As long as they're good in different places, if you put together the best parts of every human, you can get a kind of a superhuman Frankenstein policy. And that Frankenstein policy might be very, very good. It might be a lot better than any person by themselves. It's sort of taking like all the people that produce the data and unifying them in their strengths and discarding their weaknesses. That's a very powerful idea. That can get you a really, really good policy in principle. So if you have algorithms that properly perform RL, that properly perform dynamic programming, you should be able to take this idea much further and get near optimal policies from highly suboptimal but diverse data. And that goes really well with that principle I articulated early on. We want large data sets and large models. Let me give you an example of a situation where offline reinforcement learning can enable something that goes beyond what was seen in the data. Let's say that you want a robot to be able to pick up an object from a drawer. And maybe you have some training data for the robot picking that object up from an open drawer, and it does really well. Of course, if at test time the drawer is closed, the robot will have no idea what to do. So all that experience of picking up the object from an open drawer didn't prepare it for this situation. But what if we have prior data, and that prior data doesn't involve picking up the object at all? The prior data just involves a variety of other skills, none of which show picking up the object, but they show other stuff like opening the drawer, closing the drawer, moving some other objects out of the way, basically other stuff that could potentially be useful, but is not the skill that you actually want. Well, in principle, an offline RL algorithm should be able to put these pieces together. It should be able to figure out that a state where the drawer is open is good, because when the drawer is open, it knows how to pick up the object. Therefore, prior experience that gets it to that state, such as opening the drawer, is also good, even though it has never seen a single episode where the drawer is opened and the object is taken out. So we can use this idea with a standard offline RL method, nothing hierarchical, no explicit skill discovery, just pure offline RL, and you can get a robot that will pick up the object from an open drawer, but also if the drawer is closed, it will open the drawer and pick it up. It has never seen a complete trajectory like this anywhere in the dataset. Here's one where the top drawer is open, it closes it, then opens the bottom, then picks up the object. Here, there's another object in the way. It's going to pick it up, take it away, then open the drawer, then pick up the object. All right. Now, let me tell you a little bit about some of the mathematical foundations of offline RL. So this will get more into the technical details, but I'll keep this pretty brief. I mostly just want to give you a taste for the kinds of math that's involved in offline reinforcement learning. So first, a quick primer on value-based RL methods. In RL, we have an agent, and the agent makes decisions. We call those actions, A. And the world responds with states that we call S. And it also gives you a reward called R. And what you want to do is find a policy, pi of A given S, and you want that policy to maximize the total reward that you will accumulate from the actions you take. A very useful object for doing this is something called the Q function. The Q function is a function of a state and an action that tells you if you are in state S, take the action A, and then follow the policy pi, what will be the total reward that you will receive. If you learn the Q function for a particular policy pi, then you can recover a new policy that is at least as good or better by simply taking the argmax action with respect to the Q function. So this is a way to improve your policy. This is the basis of a method called policy iteration. You can also skip the middleman and directly train a Q function that minimizes the difference between the left-hand side and the right-hand side of the Bellman equation, which is shown here. So if you can find a Q function that is equal to R plus the max over the next Q function, then the corresponding argmax policy will be the optimal policy. And this serves as the basis of Q-learning. So Q-learning essentially is trying to minimize the difference between the left-hand side and right-hand side of this equation for all states and actions. So this is the loss function for Q-learning. And the cool thing about Q-learning is that it makes no assumption about which policy produced those states and actions. As long as the dataset covers enough of the space, if you can minimize the difference between the left-hand side and right-hand side for all states and actions, then you're done. So in practice, you have a sample, you minimize it on the sample, and hope that it's correct everywhere. Okay, so does that simply solve the problem? Are we done? Can we just use Q-learning and do offline RL? Well, it turns out that there's a problem here. We actually tried to do this. We tried to do this back in 2019. We took a standard benchmark task called a half cheetah, and we collected a data set, a pretty good data set of high-quality motions. And we tried to run a version of Q-learning. In this case, it's an algorithm called SAC. And we looked at what it did. And what we found is that performance would go up a tiny bit, and then it would drop. And we thought, well, this looks a little bit like overfitting. What if we just try increasing the size of our data set? The blue curve here shows 1,000 data points. The red curve shows 1 million. And you can see they're both bad. So adding more data doesn't solve the problem. So it's not like regular overfitting. We can also ask the Q function what reward it thinks it'll get. Right? Remember, the Q function is an estimate of your reward to go, so you can look at the Q values, and that's an estimate of how much reward the algorithm thinks it'll get. And that's what the plot on the right shows. The y-axis here is a log scale, so it thinks it'll get 10 to the 7th power, but it actually gets minus 250. Whoa, that's weird. So it's massively optimistic. Why is that? Well, it turns out that there's a very deep mathematical reason for that. Let's take that Bellman equation again, and let's rewrite it a little bit. Instead of writing as a max, let's write it as an expected value under a new policy called pi nu. So pi nu is the policy that assigns a probability of 1 to the argmax and 0 to everything else. So of course, the Q value evaluated at the argmax is the max. So I didn't actually change anything. This is exactly the same equation, just written in a different way that makes it apparent that in order for this to work, the Q values need to be accurate in expectation under pi nu, which is that argmax policy. Well, if you want to know whether the Q values will be accurate under some distribution, you could ask what distribution are they trained under, because they'll be accurate under the distribution under which they are trained. So let's say that these targets are Y. What's the objective? Well, the objective is to minimize the difference between Q and Y in expectation under the distribution that produced the training data. We call this the behavior policy pi beta. So whoever collected the data, they were following an unknown policy pi beta, and we're minimizing the difference under that. So we expect to have low error under pi beta, which means we expect to have good accuracy when pi beta is equal to pi nu. But how often is that the case? The whole point is to find a pi nu that is better than pi beta, so they're not going to be the same. Even worse, pi nu is selected to maximize the Q values, which means that it will seek out adversarial actions, actions that fool the Q function into producing a large value even when it cannot be that large, just like adversarial examples. And that explains why we see this problem. That explains why the Q function thinks the values are very high. It's because the policy found adversarial actions that fool it into producing a large value. So there are a variety of ways to mitigate this problem, but the particular one that I want to tell you about today is an algorithm that we developed a couple of years back called conservative Q-learning. I want to tell you about conservative Q-learning because I think there's a very intuitive idea behind it, and it's also an algorithm that in practice works very well. So there are lots of offline RL methods, but if you just want kind of a default starting point that's pretty good, this is a good starting point. So the idea in conservative Q-learning is to directly fix this problem. If the problem is these adversarial actions that have an erroneously high Q value, what we're going to do is we're going to find those actions and explicitly push down their value so that they are not overestimating anymore. So let's say that the green curve represents the true Q function, and the blue curve is your fit. It's pretty good in most places, but if you take the max, you'll get exactly that peak with the highest positive error. So what we're going to do is we're going to take the standard Q-learning objective to minimize that Bellman error, and we're going to add a regularizer that finds a distribution over actions mu of A given S that maximizes the Q values, and will minimize the Q values under that distribution. So essentially mu finds these peaks, and then this objective pushes down on those peaks. So it explicitly finds those adversarial examples and essentially fixes them. This method works well empirically, and also theoretically you can show that if you choose the regularizer weight carefully, the Q function will not overestimate. So there's a theoretical explanation for why this should fix the problem. Now, the last 2 years since CQL came out, I've seen enormous growth in offline RL. But CQL is still a very widely used algorithm, and there are lots of methods that build on it in various ways. So I'm not going to go through the quantitative details in too much time, but I would just want to highlight a few sort of meta-studies that have studied different RL algorithms in different settings. Across a number of different studies, it's been consistently found that CQL is a pretty reliable algorithm that tends to improve over the behavior policy. So this is a quote from this study called the Near Real-World Benchmark. It says, well, surprisingly, the experimental results demonstrate that these offline RL algorithms fail to outperform either the simplest behavior cloning or the deterministic behavior policy, except CQL. So CQL tends to be fairly reliable. This is another paper that also shows that it works pretty well, and they propose some improvements. Okay, but if you want to learn more about CQL, I recommend checking out the paper for more technical details. What I want to tell you about more in today's talk is actually some of the ways that offline RL can enhance applications. So I work a lot on robotics, and in robotics we often want to do learning in the real world. So we used to do a lot of work on real-world RL with online reinforcement learning. So I want to tell you a little bit about what that process looks like. First, we would instrument the task so that we can run RL. Like if you have a robot, you have to set it up so there's some safety mechanisms so that it doesn't crash when it's exploring. Maybe you need to set up something so that it can reset the task to try it multiple times. You typically have to write a bunch of code to evaluate reward functions. So there's a lot of setup that goes into making it possible for an RL algorithm to actually be deployed to explore in the real world. And then you wait a really long time for RL to run. And oftentimes, you're not just waiting, you're actually helping the method in some way. Like maybe the robot screws up, it breaks something, so you have to go in and fix it. So that's a very time-consuming and labor-intensive process. And when you do this, maybe it won't work on the first attempt. So you have to go in and you have to change the algorithm in some small way to fix it, and then repeat this whole process. And again, wait for a really long time and do a lot of work. And even after you've succeeded at this, at the end, if you're successful and you have a working policy, and then you want to solve another problem, then you have to start this whole process all over again. So you can see that this is shaping up to be a very labor-intensive procedure just to do reinforcement learning, which in principle should be an automated system. With offline RL, the picture is very different. First, you collect your initial data set, which can come from humans, it can come from scripted policies, it can also come from some baseline policy or a combination of all of the above. And you use this to train your policy offline. And then what you might do is you might go in and you might change your algorithm in some small way if you're not happy with the result. But when you change it, you don't have to redo the whole data collection. What you do then is you just retrain the policy on the data you already have. So it's purely a computational process. And if you think the performance is not good enough, you can go in and collect more data and just append it to your data set. So you keep adding to it, you keep growing it. And if you're successful, you can keep that data set and reuse it for the next project. So the next project actually becomes easier than the previous one because you can reuse your data. Let me give you some examples of this in action in some of the previous work that we've done. This is a project that we did at Google called MTOpt, where we collected lots of data from many different tasks. We had 12 different tasks, thousands of objects, multiple robots collecting the data, months of data collection. So it was a very labor-intensive process, and we got something that worked pretty well. But then we had a new hypothesis. Could we learn all these tasks using goal-conditioned RL without manually provided reward functions? So this talk is not about goal-conditioned RL, it's about the process. So we had this new hypothesis. What did we do? Well, we didn't repeat this whole data collection, we simply reused the same exact data and then used an offline RL method to train our goal-conditioned policy to see how well it worked. And it turned out to work really, really well. So without a single episode of additional data collection, we could get a policy that could collect data that could perform these goal-conditioned tasks. And such a policy could then serve as a starting point, an unsupervised pre-training procedure for downstream online RL. So kind of much like how BERT is a kind of a universal pre-training procedure for NLP tasks, this offline RL procedure was a kind of pre-training procedure for other downstream online RL tasks, and it could speed them up quite a bit, actually. Here's another example. In 2020, my student Gregory Kahn collected 40 hours of data for a ground robot navigating through Richmond Field Station. And then about a year later, another student, Dhruv Shah, used that same exact data set without any additional data collection to get a policy that could deliver, in this case, various parcels and so on to people's doors by using gold images. So he was doing something very different, but he just took that same data and reused it for a new application. And then a year later, we used that same exact data set to learn how to search. So you give the robot a particular task in a new environment, it'll actually search through that environment, try to find where that thing is. But again, it learned how to search by looking at the same offline data set that we had before. So it's a very powerful recipe to accelerate how fast you can iterate. There are many other exciting topics in offline RL. Model-based offline RL, that's a really powerful thing. Model-based learning is a good fit for offline RL because you can use a really big model, train it for a really long time offline, and then use it online. So for example, Combo is a kind of model-based version of CQL. Similar principles apply: conservatism, out-of-distribution actions. But it's also much more practical to use huge models. For example, in this paper called Reinforcement Learning as One Big Sequence Modeling Problem, we showed that you could train a huge transformer model on offline data, and it could make really high-quality predictions and serve as a very, very powerful offline RL method. You can do multitask offline RL, where you can take data from other tasks and use it as offline data for a new task. And there's all sorts of clever things you can do about how to properly share data to make this possible. And many more things. But I want to conclude with a takeaway about future directions and open problems. So there's this dream of offline RL where you would collect the dataset using any policy or mixture of policies, run offline RL in this dataset to learn your policy, and then deploy it in the real world. But there is a gap between that and current offline RL algorithms. We've come a long way since 2020, but major open problems remain. One major open problem is a workflow. So in supervised learning, we have this really excellent workflow where we have a training and a test split. You train on the training set, use the validation set or the test set, and get a sense for how well you're doing. What's the equivalent of that in offline RL? We've done some initial work in this direction, but a lot more research is needed. Statistical guarantees. Can we show provably that methods address this distributional shift? We have some statistical guarantees for CQL, but I think a lot more research here is needed. And then we need scalable methods and large-scale applications. I talked a lot about applications to robotics, of course, because that's the primary focus of my research, but I think there's room for applications to lots of other settings like dialogue systems, data-driven navigation, driving, etc. And I think these are also topics worth exploring. Thank you very much.